Okay, yesterday we have discuss about Biot-Savart law. It's that the source of this magnetic field coming from the wire in which it flows a current I, like this. Yeah. For example, we want to consider this is the wire and this is the current, yeah? And this is the, well, you can say this P and P prime where this, in this case, we have the direction of the magnetic field out of the paper, and this is inward to the paper, to the page, okay? And this magnetic field somehow depends proportionally to this I, yeah? Okay, and with this formula 30.1, okay, this is for infinitesimal form, and for in general we have this B here. We assume that this I is constant, yeah, or depend on time. Also, we could also we use this 30.3, okay. So mostly we will use this I to be constant, this the current. Okay, this is for the example we have discussed yesterday about the wire, very long wire, where in which the current flows through this wire. Okay, and I is a constant. Just wait a moment. Okay. And then we have discussed for ring. If we have ring, for example, this one, and in the ring, yeah, we have the flow, the current, I, okay. Then we get only the X component is non-zero. Y component 0 because they cancel to each other, okay? If we calculate this one. Okay, we also have discussed about the force between two parallel wire, conducting wire, okay? And this is this F1 acts on first wire, okay? Usually this F2 also act on I2, the second wire, okay? That they have an opposite direction. Okay, but the sum is 0. So somehow this F1 and this magnetic force, yeah, is somehow like an action and reaction forces. Okay, so this is the force for F1, F2 also the same, but they have this opposite direction. So today, just a moment. Okay. So today we will discuss about Ampere law. This is analog, yeah, as the Gauss law in electric electrostatic. Okay, just consider we have. Okay, just consider we have this, for example, the wire with I equals to 0, and then this compass. This compass, it doesn't. They don't move the needle of the compass. The needles of the compass do not move. Okay, and if this this wire we flow it with the current I, for example, and these needles of the compass will be moves here. Okay, so this figure C here, if you, well, put some iron sand, it will, the pattern will looks like this circular, this one. So basically, this Ampere's law is about this closed integral B dot ds is equal to mu 0 E I enclosed. Just for example, so this is the Ampere's law. For example, if let's say not this one. If we consider, for example, very long wire, Celine, sorry, just a moment. Okay, let's continue. So, for example, if you have, let me, I have to draw at the end. Okay, for example, this is the wire. Okay, this is the line, Ampere's line. Okay, this is the I here. I enclose. In this case, I enclose is I, okay? So the integral B dot ds equals to mu 0 E enclosed. Okay. So this should be B times 2 pi. Let's say this is R here. Okay, this should be 2 pi R. And this is mu 0, the I enclosed is I. Okay. So we get exactly for very long wire magnetic field of very long wire. Okay.
Sir?
Yes?
Sorry to interrupt. Hamadi had some problem with his connection, internet connection.
Okay. Okay. That's for very long. Just a moment. With the PDF book. Okay. So that's the example. So basically, similar as the Gauss law of electrostatics, this Ampere's law is more general, yeah, than Biot-Savart law, but it is easier to solve the Ampere's law using symmetry. Like the very long wire, it has cylindrical symmetry, okay? So that's why it is easier to do. But using Biot-Savart law, it's very long. Yeah? It's not so easy. Yeah. So that's the problem. So you can use our Biot-Savart law or Ampere's law. Okay, both, but depends on the problem. Okay. So I will discuss about the second example of the application of the Ampere's law. It's a very long wire also, but it has a radius. The radius, it has the radius R, capital R. And in this wire, it flows the current, okay? Current, and the current distribute uniformly. It means that the current density is constant, okay? So for R greater than capital R or equal, we could get the same as this very long wire as I've shown you just now, okay? this 3014. So this is the magnetic field outside the wire. Okay. What about the magnetic field inside the wire? So if you consider this little circle, this second circle here, this the big circle is the first one, and this is the second one. Okay, we get this E enclosed is I prime. Okay, the I prime, the comparison of I prime over I is proportional to the radius r squared, okay, over r, capital R squared, okay. So we get the relation between I prime and I, okay. I is the total current, yeah, that flows in the wire. Okay, so we get that this I prime here is equal to this one. So from this left-hand side, we have this B2 pi R, and then we get for R less than capital R, we get this formula 30/50. Okay, if we draw B against R, then we get this graphic, this picture. Okay, this is linear. It's proportional to R, and this is proportional to 1 over R. Okay, this is outside the wire, and this is inside the wire. Any question? Okay, if not, I will continue. So, for example, we have this toroidal. Toroidal, well, toroidal is device. It's circular, but what is it? It consists of a conducting wire wrapped around the ring. Okay, the torus. So you have a torus, and then you wrap this torus by a wire, conducting wire. Okay, that's toroid. So even if in the picture it is not an ideal toroidal, so this wire wrap it so very tight. Okay, so there is no space. The space between this wire is zero. Okay, it's very tight. Okay, so there is no magnetic field outside this toroidal. Okay, the magnetic field, the non-zero magnetic field exists only inside the toroidal. Sorry. Okay, so if we do this, okay, we will get this. Sorry. This amperes line is the blue one here. This is exactly in the center, well, let's say in the middle, yeah? In the middle of this toroidal, okay? Inside the toroidal, then we get this E enclosed. E enclosed is N times I, okay? So we get this 30/16 for toroidal. This is the magnetic field inside the toroidal. Okay, because outside, because we have the ideal toroidal, so the magnetic field outside the toroidal is zero. Non-zero only inside the toroidal. Okay? Any question? Any question? No. Okay, let's continue. So this is the current from the infinite current sheets. For example, you have a plate. Yeah? Plate, this is the cross section. This is plate here. And on the plate, we have a current, yeah, with density Gs. Yeah. Gs is the density of current per length, I think. Yeah, per length. Okay, so we have here on the right hand side of the plate, okay, we have this magnetic field up, and then the left is down, yeah, okay? So we get that from Ampere's law, we get this 2BL. Why is 2BL? Because the S here, the L here is parallel to this B, and on the left hand side, this the L is parallel to B, okay? That's why this is 2BL at the end. So En close is GS times L. Yeah. We suppose this to be L, and then we get that this B here is mu 0 GS over 2. Okay, it's similar like the electric field around this infinite sheet or plate, yeah, in which the plate has the density per area, ya, di current di charge density per area. Okay. And this is you can see that this is the magnetic force on the current segment. So this is the current segment here. This rectangular, it has I2 here. The current flows through this segment, the wire segment. Okay, and this is the wire, yeah. This wire 1, this is wire 2. Okay, so the force of the magnetic force. Okay, let's say this B first, yeah. This B, here is from this very long wire, okay, and the distance between this disk and, for example, to a point in the rectangular, we call it X. Okay. So this is on the right hand side, the magnetic field of wire 1 is inward, yeah, inward of to the page. Okay. Then on the left hand side, it's outward, yeah, away from the page. So we get that because this should be L cross B, okay, IL cross B. So this L is minus K, but I here is to the I, okay. This I2 here, this in this segment, okay. This in this element here, okay, this should be 0, okay, because this L cross B, just a moment. Just a moment, yeah. Continue, okay. The task is to find this magnetic force exerted by wire 1 on the top of wire of length B. So in this one, okay. So it should be this one. Okay. So the total should be from A to A plus B, okay, the integral. So we get this one. What about this, what is this? The force exerted on this wire? Hello? This is equals to, the magnitude is I1 times I2 mu 0 over 2 pi. The distance between them is A plus B, okay, in this case. So it's a constant. Yeah. Okay. It's not integral. Okay. Do you know the direction of the force in this line? Reno. Hello.
Yes, sir.
Yes. The direction of force at this line. This from top to down.
I'm sorry, what was the question again, sir?
The question is the direction of the force, the magnetic force
Oh, sorry, it's to the
on
right.
yeah, on this line. This line, you see this line?
Yeah. It's going to the right.
Where?
sir.
Where?
It's going to the right, sir?
Sorry?
To the right.
To the right. Uh, yeah, yeah. Okay. Thank you. Any question? Okay, let us continue. So let us move to magnetic field of solenoid. The solenoid is terms of wire, yeah. Yeah, so it's a long wire wound in the form of the helix. Okay, you can see the picture here. So in reality, if we have a solenoid in general, it is not an ideal solenoid, okay? Because we have somehow the gap, yeah, between the first coil and the second coil, okay? The first wire, then the second wire, okay? So because have a gap here, so there will be a leak, yeah? A leak from this one. So it will be there will be a local magnetic field, yeah, if in reality, okay. But in this case, in this lecture, and also for examination, this solenoid is an ideal solenoid, which means that we wrap the wire, okay, it's very tight, okay, such that there is no gap. The gap between the wire is zero, okay? So there is no magnetic field, the leaking of the magnetic field, yeah, outside this one, okay? So this is not an ideal, so this is the ideal, this ideal solenoid, okay? So the magnetic field exists only inside the solenoid. Outside the solenoid is zero, okay? Because there is no gap between the wire here. Okay? If this is the case, then we get that using the Ampere's law, like this. So this is B times L inside the solenoid. And because the B is zero, so this should be zero, okay? So this BL only only inside the solenoid, okay? Then I enclose how many wire you have to enclose? This N times I, okay? The current that flows in the wire, okay? So we get this formula. So this is for ideal solenoid, okay? N over L, N is the number of the web, okay? The number, yeah, of coil, yeah? And L, this L here is the length here, or the length of the solenoid, you can say. Okay, usually if in ideal solenoid, we have the density of, what we call it, yeah, and little n here. The density of solenoid, yeah, of the wire, yeah, of the wire. Okay. Any question? Any question?
Sir, what
Yes.
was the small n stands for again?
Small n here.
Yeah.
This one.
Yes.
N over L. It's something like the density of the number of the wire per length.
Okay. Okay. Thank you.
N is the number of wire that wraps this capital N. Okay. This little n is the density of the number of wire per length. Okay, let's move to the magnetic flux. So similar to electric flux, yeah, this E times dA for electric flux or magnetic flux, we just replace this electric field by magnetic field, okay? So we get this one. This in general integral B dot dA, where Vb, the magnetic flux, is Ba cos theta. Okay, so this is this dA here, and this is this B here, flows through the surface, yeah, whose the area is A. Okay, this is A here, is normal. B dot dA in this case is not zero. But in this case, because it is perpendicular to this A, then B dot dA is equal to zero. Okay? This is parallel, this is perpendicular. So this is, for example, if we have the, so we have this very long wire. Okay, and this it has, and we put around this wire a rectangular loop, yeah. This rectangular, okay, like this. So how many flux? So how to calculate flux that passing through this rectangular? Okay. So it is similar as above the computation. We have this B mu 0 I over 2 pi r, where r is the distance between the wire and a point in the rectangular, okay? But the point in the rectangular, we could define the infinitesimal of area of the rectangular called dA here. dA here is B times dr, okay? Then we get that from, well, we could use the integral, okay, integral from C to A plus C. So we get that the flux, total flux of the magnetic field that passing through this rectangular loop, the formula is this one, okay? Okay, this is what I call, this is our dipole magnetic. Sorry, this is magnetic dipole, and this is the electric dipole, okay? It's similar, okay, but not the same. So basically this is, oh, this is outside our material. Okay. This is magnetic field in the matter, yeah. Somehow you have to modify it. This B here is mu 0 times H plus M. This H is magnetic field, okay. This M here is the magnetization. So somehow for similar as in the electrostatic case, we have this M is proportional to this H, okay, times psi, okay, C, okay, C. This is called so-called magnetic susceptibility. So this is in general. Okay, no paramagnetic. Okay, no ferromagnetic. Okay, so the material who has very strong influence, if we turn on the magnetic field, is called ferromagnetic. Below them, below it, it's called paramagnetic substance. Okay, a material, paramagnetic material. You see that this susceptibility, magnetic susceptibility is 10 to the 5, okay, minus 10 to the minus 5, okay. This indicates paramagnetic substance. And for negative one, we get this diamagnetic substance, okay. Unlike this dielectric constant, the electric constant is always positive, but in this magnetic case, we have this diamagnetic susceptibility is negative, okay. This is a ferromagnetic. Okay, this only is short material, okay. So this is what I told you yesterday, okay. This illustrates this so-called Meissner S effect, yeah? That the superconductor, a superconducting material, will levitate, yeah? If we took this below is a magnetic field. Okay, it will levitate over this L here. Okay, this magnetic field of Earth is very, very weak. Okay, any question? Any question? So far, no. Okay, we will continue, yeah, to this magnetic induction. So Faraday laws of induction. So this should be okay. So we have a magnetic rod, for example. If you move it toward a coil, for example, yeah, and then it has a current, okay. This indicated by the needle of this amperemeter moves. Yeah, there is something like somehow called this electric current induction. The induced electric current, okay, the induction of electric current, okay, and the direction like this. So somehow, why the current like this? Because the induced electric field, sorry, the induced electric current will also produce the magnetic field, the induced magnetic field that against this magnetic field, okay? So, okay, I will explain in the whiteboard. Okay, we have this coil, and this is the magnetic field. This is NS here. Okay, so the magnetic field is outward, yeah? Like this, and this is inward. Okay, if we move this magnetic rod to this one, let's say for a constant velocity or constant speed, okay, this wire will produce an induced magnetic field that is against this magnetic field of the rod. Okay, what is against that, such that the induced magnetic field it somehow repel the magnetic rod. So it should be, the direction is like this. So this is the induced magnetic field. So the red one is magnetic field, but the blue one is the induced magnetic field. Okay. If you use your right hand, you will get that the current will flow to this one. Okay. Somehow they produce the induced magnetic field that repel this magnetic rod. Is that clear? Or not clear? Which part, which are not clear? Hello? Okay. Let's stop here. I will continue with the book. So if you move towards this coil or this wire, okay, this curved wire, it will be induced, there will be an induced current such that this induced current produce the induced magnetic field that repel this rod, okay. Somehow the direction of magnetic field is against this magnetic field. Somehow it will produce the magnetic field with the same pole, okay. This is N and this is also should be N, okay. But if you move away this magnetic rod, the current will flow the other way around, okay. Somehow it becomes the south pole, the induced magnetic field, okay. If you know what I mean. The simplest thing, if you know about, well, in bahasa we call it benci tapi rindu. Jadi kalau dia itu dekat selalu berantem gitu ya. Karena ini sifatnya melawan, sedangkan ketika jauh dirindukan gitu. Saling telepon, tarik menarik, kurang lebih seperti itulah gambarannya. Hope you understand. Okay. So, if this is the case, then we have the induced voltage. Okay, this induced voltage is equals to minus the change of the flux over with respect to this time. Okay, this Vb is the magnetic flux. This minus here shows that this epsilon, the induced electromotive force, is against this the original magnetic field, okay, this minus. So we get like this one, minus d over dt, Ba cos theta. I will give you an example. Sekitar not this one. So this is the example. Oh, I forgot to tell you. in the picture, in the first picture above here, A picture, figure 31.1a, it means that the flux it becomes stronger, okay, becomes stronger. So the flux increases, okay. In this case, the C, the flux is decreased, okay. So if we go to this one, okay, we have the road here, okay. So this is the L here, the length of this circuit. We have the resistance, okay. This all of them made from a conductor. So if we move this road, yeah, to the right with this F here, I mean this F here is applied to this one, okay. So the flux is increased in this case, okay. So if the flux increase in this case, then the induced magnetic field should be toward us, okay. This is coming out from this paper, okay. So if you use your right hand, you will get that because inside this loop, rectangular loop here, the magnetic field, the induced magnetic field is moving out of the page, okay. So you will get the direction of this current is to the left in this case, yeah, like this, okay. If you apply it like this, the flux becomes bigger, okay, become much bigger, increasing, the flux is increasing, okay. But if you, is there any, not yet. If you push to the left, okay, so the flux is decreasing, okay, and then we will get the direction of this current, okay, is in this case is the other way around, okay, from the left to the right. Okay, that's for now. I will summarize the lectures today in bahasa, okay, starting with Ampere's law. Oke, jadi kita kemarin sudah bahas tentang hukum Biot-Savart ya. Jadi hukum Biot-Savart itu analogi dengan hukum Coulomb ya di mana? Di apa namanya di elektrostatik ya. Nah, ini cuma bedanya hukum Ampere ini ya. Itu bentuknya seperti ini, mirip seperti hukum Gauss gitu ya. Ini integral tertentu B dot ds itu sama dengan mu 0 enclosed, I-nya mu 0 I enclosed, oke. Nah, I enclosed di sini. Nah, kita ambil contoh tadi itu untuk apa namanya? Untuk yang ini ya. Apa kawat yang sangat panjang gitu ya. Jadi atau dikatakan R-nya itu jauh lebih kecil dibanding dengan L. Jadi jarak antara kawat dengan yang mau ditinjau medannya itu jauh lebih kecil. Sehingga nanti dari sini kita punya simetri silinder sehingga kita bisa dapatkan seperti ini. Oke? Jadi itu dengan simetri silinder. Kemudian kita juga meninjau untuk yang apa namanya wire, tapi dia ada radiusnya, tapi arusnya ini itu terdistribusi merata di seluruh daerah dari kawat gitu ya. Jadi kita meninjau yang di luar kawat itu sama dengan ini. Jadi ini kawatnya juga sangat panjang. Jadi kita akan menghasilkan hal yang sama untuk R kecil lebih besar atau sama dengan R besar. Jadi di luar kawat. Ketika di dalam kawat itu kita pakai perbandingan. Jadi yang kita mau tinjau di sini, di dalam ini, yang lingkaran dalam ini, itu adalah I prime. Jadi I prime dibagi I itu adalah PR kuadrat luasnya dibagi dengan luas total dari penampang kawat ini, ya, penutup kawat. Gitu. Jadi didapatkan seperti ini. Nah, I enclose-nya itu adalah I prime dalam hal ini, karena kan kita cuma dapatkan yang di dalam ini aja. Oke, jadi cuma yang di dalam ini. Sehingga kita dapatkan I prime di sini. Nah, I prime di sini adalah sama dengan R kuadrat per R besar ya, kuadrat. Jadi kalau saya masukkan yang seperti ini 2πr, saya dapatkan B di sini ternyata sebanding dengan R. Oke. Jadi gambarnya seperti ini. Yang di dalam kawat itu sebanding R, sedangkan yang di luar kawat itu 1 per R. Oke. Kemudian kita juga meninjau, mengaplikasikan istilahnya hukum ampere itu pada kasus toroidal. Jadi toroidal itu gambarnya seperti ini. Walaupun ini kelihatannya ini bukan toroidal ideal, tapi ini kita asumsikan toroidal ideal ya. Jadi kawatnya itu dililit ya, di wrap gitu secara rapat gitu ya. Sehingga tidak ada medan magnetik yang bocor keluar. Sehingga medan magnetik itu cuma di sini aja. Di dalam ini itu tidak ada. Oke. Sehingga untuk medan magnetik yang di dalam, tepatnya di pusat ini yang di garis biru ini, yang di pusat dari toroidal di dalam itu didapatkan seperti ini, di mana N di sini adalah terkait dengan jumlah kumparan pada toroidal. Oke. Kemudian ini contoh pada plat yang berarus ya. Jadi kita punya arus tapi dengan rapat arus perpanjang yang disebut JS di situ. Ini memang analog dengan ini yang rumus medan listrik di muatan yang bidang yang sangat luas itu juga sama seperti ini. Kita juga menggunakan hukum ampere didapatkan seperti ini. Kemudian ini menghitung gaya ya dari sebuah kawat ya, kawatnya itu yang cuma ini aja gitu ya. Yang horizontal, sedangkan yang vertikal dia kan konstan. Oke. Jadi kita ambilnya tuh DFB di sini. Kalau yang di sini mah konstan. Kemudian kita membahas juga tentang solenoid ya. Jadi ini solenoid yang tidak ideal, yang secara realitas dia ada jarak antar lilitannya. Oke. Kalau ini ada jarak itu berarti nanti akan bocor istilahnya gitu. Jadi akan ada medan magnetik yang bocor. Nah, kalau dia itu kita buat serapat mungkin, ya, kalau yang ini masih belum rapat ya, jadi ini masih ada yang bocor medan magnetiknya yang di sini. Kalau dia itu rapat, itu berarti seperti ini, yang digambar ini. Jadi medan magnetik di luarnya itu 0, yang ada cuma ini. Makanya ini kita dapatkan rumus seperti ini. Ya, dengan menggunakan hukum ampere. Kemudian kita juga belajar flux, yang flux magnetik. Ya. Jadi flux magnetik itu seperti ini yang tidak 0, sedangkan yang 0 itu adalah yang tegak lurus ya. Seperti itu. Nah, contohnya kita menghitung flux dari loop yang berbentuk persegi panjang. Ya, jadi berapa flux yang di dalam ini. Kemudian juga kita membahas tentang momen dipol magnetik ya, yang seperti ini, sebelah kiri, sebelah kanan adalah dipol listrik. Oke. Jadi ini sebenarnya modifikasi hukum ampere, saya tidak akan jelaskan karena ini di luar silabus ya, Anda bisa baca. Tapi yang jelas kalau dalam bahan itu kita mengenal ada H, yang di H itu disebutnya medan magnetik, sedangkan M di sini itu disebutnya magnetisasi. Magnetisasi itu adalah momen magnetik per unit volume. Magnetisasi. Nah, kalau dia itu linier, itu berarti magnetisasinya sebanding dengan medan magnetik H. Yang dimana si di sini, biasanya si M, itu kita biasanya disebutnya magnetic susceptibilitas magnetik. Nah, ini contohnya ini untuk paramagnetik, dia biasanya sangat kecil, memang -5, sedangkan untuk diamagnetik dia minus dan sangat kecil artinya. Kalau dia itu ferromagnetik itu bisa sampai ratusan atau ratusan ribu ya, atau 10⁴ lah kebalikan. Jadi paramagnetik itu yang sifatnya bagus terhadap medan magnet ferromagnetik. Dan memang umumnya logam. Kemudian juga kita bahas, nah ini contohnya untuk yang superkonduktor ya, yang melayang di atas magnetik. Jadi superkonduktor ini yang kemarin bisa saya bilang itu dipakai untuk aplikasi kereta cepat ya, yang misalnya tanpa hambatan. Kemudian udah kita bahas. Nah sekarang kita membahas tentang induksi magnetik. Ya. Jadi induksi magnetik itu terjadi ketika apa? Kita mendekati atau menggerakkan medan magnet batang magnetik ke sebuah kumparan gitu ya. Sebuah kumparan. Jadi kalau kita mendekat akan menghasilkan arus induksi. Nah, arus induksi itu dia harus melawan dari batang ini. Kalau batang ini north ya berarti north itu utara. Nah, berarti dia akan menghasilkan arus sedemikian rupa sehingga arus ini akan menghasilkan medan magnetik induksi yang melawan dari batang magnet ini, berarti dia harus sama kutubnya. Jadi arahnya ke kanan medan magnetiknya. Jadi penolakan gitu, ada penolakan. Sedangkan kalau dia itu menjauh, itu berarti dia ada penerimaan gitu ya, tidak melawan. Seperti itu. Ya itu seperti itu yang tadi saya bilang, benci tapi rindu ya. Dekat berantem terus, jauh dirindukan gitu ya, sering telepon segala macam. Hanya analogi. Jadi, nah di sini kita membahas tentang, jadi yang peristiwa tadi itu dirumuskan oleh Faraday dengan hukum induksinya. Ini bentuknya seperti ini, epsilon itu adalah tegangan listrik induksi atau induced electromotive force ya. Ini sebenarnya minus dari perubahan flux dibagi waktu. Tanda minus di sini itu menandakan dia melawan. Kemudian ketika ada n buah lilitan, itu tinggal dikalikan aja. Jadi dapatnya seperti ini. Dan kita dapatkan BA-nya, V-nya ini adalah BA cos theta. Mungkin itu aja, kecuali kalau Anda ada pertanyaan, kita akan lanjutkan minggu depan ya. Ya Jumat kan ada tutorial. Tutorial juga bisa nanti saya isi materi untuk percepatan. Kalau mungkin yang di sini itu masih terlalu lambat gitu. Saya sengaja mungkin nggak pakai whiteboard karena kalau nulis itu terlalu lama gitu ya. Sedangkan kita sekarang itu harusnya sudah sebentar kolaborasi biasa apa itu kita sudah. Oke, sekarang harusnya memang sudah sampai ini induktansi ya. Induktansi atau induktor ya, should be. Okay. Any question? Any question? If not, I will end here. Okay.
Not yet, Pak.
Yeah? Hello?
Not yet, sir.
Okay. I will end right now, yeah? Okay, let's stop here. Thank you. See you on Friday, yeah?
Thank you, sir.
Remember Friday. Okay.
Thank you, sir.
Okay, thank you.